Titanium melts at 1,668 degrees Celsius. Inside this factory, they forge it at 1,700 degrees Celsius, and it doesn't melt. At that temperature, steel would evaporate, aluminum would ignite, and humans could not stand within 10 meters of the heat. Yet, this is where modern flight begins, in a chamber of controlled fire. Every turbine blade in a jet engine must survive forces that would destroy almost any other material. 15,000 rotations per minute, temperatures close to the surface of the sun, and pressure that crushes mountains. If one blade fails, the entire engine disintegrates. So how do they create a shape that can survive inside a living flame? The answer lies not in brute strength, but in microscopic control of atoms. In this factory, heat is not the enemy, it is the tool. You think this is the limit, but this is where it all begins. The process starts inside a sealed vacuum chamber. Chunks of raw titanium and aluminum vanadium alloy are dropped into a crucible made of ceramic and quartz. Inside, the plasma arcs ignite lightning made by man. The metal liquefies in seconds, forming a molten sphere brighter than daylight. Hydrogen, oxygen, and nitrogen, the three invisible killers of titanium, are sucked away by vacuum pumps. If even a single molecule of oxygen touches it, the batch is ruined. From this furnace, the liquid metal flows into graphite molds, shaping the first rough ingots. As the surface cools, it turns a strange silver blue, the color of purity achieved under pressure. The real forging hasn't begun yet. This is only the metal learning to breathe. Miles. The solid ingot is reheated to nearly 1,200 degrees Celsius, hovering on the edge of transformation. Massive hydraulic presses rise above it, 8,000 tons of force descending through the air like gravity multiplied. Titanium is crushed, stretched, and rotated again and again, each blow refining the internal grain. Every strike is measured to the millisecond. The goal isn't just shape, it's texture. The microscopic alignment of crystals that decide strength and fatigue. As heat and pressure combine, the metal glows white, then fades into dull orange. Operators watch through protective glass. One mistake, too hot, too fast, and the titanium turns brittle. But when done right, the billet takes its first true form, dense, uniform, flawless. When metal almost melts, what keeps it whole is precision, not power. Inside another chamber, the forged billets rest on ceramic trays. Here, temperature is no longer the enemy, it is the surgeon. Titanium's atomic lattice can exist in two worlds, the alpha phase of solidity and the beta phase of flexibility. By heating and cooling with surgical timing, engineers freeze both structures together, a dual-phase balance that gives the blade its resilience. Water quenching drops the temperature from 900 degrees Celsius to 20 degrees Celsius in seconds, trapping the microstructure mid-transformation. What follows is tempering a slow reheat to relieve internal tension. Every atom aligns under invisible command. Even when the fire ends, the transformation continues within the metal itself. Now the metal meets the blade of another kind. 5-axis CNC machines carve the cooled titanium block into aerodynamic perfection. Each cut removes mere microns of material, forming the exact curvature needed for airflow at supersonic speed. The coolant streams shimmer under white light, cascading over cutting tools spinning at 20,000 revolutions per minute. Sensors detect vibration at the atomic scale, adjusting path mid-rotation. The final geometry is defined not by eyes, but by math. When the cutter retracts, what remains is the skeleton of flight. A single titanium wing, smaller than a hand, lighter than air, stronger than time. You think forging is done with fire, but real forging happens with algorithms.
Laser scanners map the surface topography, generating a 3D model on screen. Every micron recorded, no deviation detected.
The blade enters another chamber, surrounded by robotic arms. Each nozzle sprays molten ceramic particles at 10,000 degrees Celsius, forming a thermal barrier coating just 200 microns thick. The plasma arcs like miniature suns, blue, purple, and white. Layer by layer, the coating bonds with titanium, sealing it from oxygen and flame. This invisible armor allows the metal beneath to stay cool even when the surrounding air exceeds 1,700 degrees Celsius. Every surface is inspected with laser reflection, not one particle out of place. The strongest protection isn't heavy armor, it's a layer thinner than a strand of hair. The finished blade is locked into a turbine test rig. Hydraulic clamps tighten, the chamber seals. Then, silence. A low hum grows until the metal begins to sing. At 15,000 revolutions per minute, the titanium bends, expands, and screams in frequencies humans can barely hear. Laser sensors record every micron of deflection. The readings appear on screen. Perfect balance, no deviation. Here, strength is not a number, it's rhythm. Each atom vibrates in harmony with every other. When the blade reaches its limit, what keeps it from shattering is the order within chaos. Weight, 320 grams. Tensile strength, 950 megapascals. Operating temperature, 1,700 degrees Celsius. Rotational speed, 15,000 revolutions per minute.
Result,
No emotion,
PASS,
no margin for error.
15,000 RPM
Just data
stability.
forged in fire, confirmed by silence. In this factory, titanium does not melt. It obeys. And within every engine that cuts through the sky, a piece of that obedience still burns.